has over 20 years' experience working with technology companies in Silicon Valley. Prior to founding Pelican Imaging, Kartik headed computational cameras at Micron Imaging. He spearheaded the design of extended depth of field imaging systems for the mobile camera market. As manager of the camera and scene modeling group, Kartik's end-to-end simulation environment for camera systems, architecture and module simulations has been adopted in parts of the mobile imaging ecosystem. Previously at Intel, Kartik was principally associated with investigating medical imaging and visualization between Johns Hopkins Medical School and the Institute of Systems Science in Singapore. His interests include image processing, computer graphics, visualization, computer architectures, and medical imaging. Kartik founded Pelican Imaging in 2008. He received his PhD in computer science from the University of California, Santa Cruz. He also holds a Master's of Science in Computer Engineering from the University of Massachusetts, Amherst, as well as a BTech with honors in electrical engineering from the Indian Institute of Technology, Kharagpur. Will you please welcome Kartik Venkataraman?
If you look at how the cameras have been evolving in the cell phone space over the last few years, it's really been all about megapixels. The problem is there is not a whole lot of real estate on the cell phone. There is really a constraint on how big of an optics you can have. The optical format is kind of fixed because the moment you make an optics with a large aperture, then the height of the optics also increases inordinately. And that kind of puts pressure on the cell phone form factor because the industrial design constraints often prefer a thin smartphone. Right? So the only way to get around that is to continue to sustain the perception of improving quality through feeding more megapixels is to shrink the pixel scale so you can fit in more of the pixels in the available area. And you do get some benefits. Every time you shrink the pixel, you increase the resolution marginally, but only up to a point. And because beyond that, you're sampling at such a fine rate that you end up with an optically limited system. The optic simply does not have the frequencies that it's passing through to enable the smaller pixels to take advantage of it. So as a result, you then have to get around the optically limited system, you have to increase the number of lens elements. For example, if you look at the iPhone 5S or the Samsung Galaxy S4, they now have 5 or 6 lens elements in their lens stack. And that increases the overall thickness of the camera module, which often is a limiting factor in how thick your phone is today. And the other thing, of course, to note is, continuing to shrink the pixels in this way, we are down to 1.4 micron pixels okay, on the cell phones that you have today, going down to 1.2 and probably down to 0.9 is not really sustainable from a physics point of view. Your wavelength of light, visible light, extends from 400 nanometers to 700 nanometers. And that's in microns, it's about 0.7 microns. Your pixel size is today at 1.4 microns, going down to 0.9 microns. So you're getting right down to the point where diffraction effects overwhelm the ability to get the light down to the photodiode on the pixel. So you can't really go down much further. And not to mention the fact that you shrink the pixels down, you're also losing light sensitivity. The pixel, while it may be sharper, is not as sensitive to light, and that's a problem. So if you look at how the cameras evolved in the industry, we started up, the fundamental camera architecture has not really changed in 100+ years. It is still the same pinhole camera that we had when cameras first came in to the market back in the late 19th century. So you have the black and white pinhole camera essentially, which records the intensity of light, and it averages all the wavelengths, the visible spectrum. So what you get is simply the white light that you're recording the intensity of. And as the industry evolved a little bit, people figured out how to capture the color. So this now captures the intensity changes with wavelength. So you add another parameter to the parameterization. So you have x, y, and spatial coordinates of the scene that you're trying to capture along with lambda to the wavelength of light. And then, of course, the color moving camera came into picture. So you're adding the time dimension as well. But if you look at most cameras today, that's really where it stopped. But there's a lot more to the scene around us than just the spatial coordinates and the wavelength of light in the visible spectrum. So for instance, if you were to cover a region in space with multiple cameras, then you could potentially capture the scene from different points of view. And then you have an additional parameterization, which is the coordinates of the viewing position of the camera, because that's also changing depending on where you capture the image from. So if you look at the idealized, if you have the luxury of having an idealized holographic movie camera, then you would be able to reconstruct from every possible view, at every moment, and every position, at every wavelength, within the bounds of the certain region that you're considering in terms of space, time, and wavelength. But that's really a lot of information. In contrast, the camera of today is capturing but a small portion of this information around us. It is capturing the two-dimensional slice of this multi-dimensional universe that we are living in. So it's fairly limited, and I think the question that has to be asked is, are we leaving something on the table? Is there ways by which we can improve the consumer experience in ways that go beyond what we are doing today? So how do we evolve the camera architecture? So what is the right architecture for mobile devices? In a sense, we are taking an architecture that was not really meant for a small form factor device, such as the mobile phones that we carry around in our pockets today. And we are trying to shoehorn or fit that into that form factor. And it's we're getting to a point where it's not really scaling well anymore. So the question is, what else can we capture and how do we do it? Multi-spectral, which means you can go beyond the visible. But if you did, what does it give you? How does it improve the overall experience? We see in 3D, we see depth. We have two eyes. It gives you the ability to triangulate and assess the depth of the scene around us. But we are still stuck in a 2D world as far as imaging is concerned. And then what is the impact on consumers that we must consider? You obviously need good resolution, but beyond the resolution aspect, the color gamut, how good is the color? So for example, if you were to take a picture with your cell phone in this limited lighting environment, most of the photographs you would get would be fairly noisy, and the colors would actually be quite desaturated, which they do on purpose, because if they're trying to capture the color quality at this light level, you are going to be amplifying the noise, which is noisy enough as it is. And then, of course, there is value in 3D. We'll go into it in a little while. And low light is clearly an area that cell phones still have a lot to do. So what I'm going to show you is an architecture that can address all of these problems and help us improve some of the limitations that we have today. And in a very small form factor that allows you to scale very well on a limited form factor device. So what we do is we're saying that rather than have a single large lens, you divide up the available space into a number of smaller lenses. And so you have a multi-aperture system. And you ensure that each camera now in the array is optically isolated from the other cameras. And it gives you some advantages, as you'll see in a while. So in this picture, you can see that if you have, see where the mouse is. There you go. So object, depending on where the object is in front of the camera, depending on the distance that the object is, the image of this point on the cameras in the array are displaced from the optical axis of each camera, more or less, depending on the distance of the object in front of the camera. So for instance, if you have an object very close to the camera, the offset from one camera, the position of one camera to the location of that same pixel in the other cameras in the array is significantly larger than if the object was much further away. And this gives you, by triangulation, you can actually correlate the distance to the object just simply by determining what the offset, or the disparity as we call it, between the corresponding pixels in the different cameras in the array. So depth comes naturally. And there's a corollary, because our eyes are able to triangulate the depth, because by virtue of the fact that you have two eyes. But the array camera actually has an advantage over a two-camera system in that it is much more robust in the presence of noise. In a two-camera system, there is, when you're trying to match pixels in one camera with the other camera, in low light situations, because of the noise, the match is prone to errors. With multiple cameras, the more cameras you have the advantage of having a certain amount of robustness. Now the cameras are all optically isolated, which means that you can now sense the different colors of light. So you can have the red, green, or blue, which are the primary colors which you sense color. But you can also go beyond that. You can go into the near IR spectrum. And there are some benefits to doing that, even in the consumer space. Unlike in the legacy cameras where, you have an IR cut filter that filters out all the infrared components. So you want to sense only the visible light. There is the problem that if you were to allow the near infrared into the sensing device, you will end up corrupting the color in the process. By optically isolating the different spectra, we have a chance to ensure that that corruption doesn't happen, and that yet have certain advantages by sampling beyond the visible. And finally, of course, these cameras are all independently controllable, which means that I can change the exposure of these cameras as well as the trigger times of these cameras. And this has some benefits in that you can capture dynamic range information, or for instance, enable high-speed video by triggering these cameras at slightly different phases in time. So here's an exploded view of the camera system that we built as a reference camera. And it consists of a lens housing to protect the lens array, a spacer that separates the lens from the sensor, the cover glass that is typically used to protect the sensor from contaminants, and the whole assembly is mounted on a PCB, and you have a fairly thin device. You'll notice here that there was no actuators for autofocus, which is present in most of the cameras today. The reason is, given the fact that you're now taking the conventional optics and dividing them into a much smaller optical aperture, and the corresponding focal length is also reduced, These together have the effect of pulling in the near focus substantially to the point that what you capture is all in focus to start with. So there is, as a result, you don't really have a need for an actuator, which is another benefit. You don't have the problem of an autofocus lag. We've all experienced a situation where you try to capture something quickly and you find that the moment has passed because the autofocus hasn't settled. So there are several things that have to happen, of course, for all of this to become a reality. And one of that is really the optics. The technology to do optics arrays has really come a long ways in the last decade, in that there are technologies that allow you to fabricate the optics as arrays on a wafer, much like silicon chips. They use a glass substrate, much like what you see here, and they fabricate the polymer surfaces on either side of the glass substrate to fashion a lens element. And they can stack multiple of these glass substrates one on top of the other, and then you dice the arrays in one shot. So this gives you an exploded view of the lens stack, where you can have multiple glass substrate elements separated by spacers. You can even have an aperture, for example, that allows you to control how much light enters the optical stack. So the question that comes to mind immediately is, if you're going to reduce the size of the optics in terms of the aperture size, then it's fairly intuitive to notice that the amount of information that you're trying to capture with that optics is much reduced. And while resolution is not the only thing that's important, it is clearly important from a consumer point of view. And the question becomes, when you end up reducing or downsampling the resolution by using a smaller optics, how do you get that resolution back? Now, if you look at this picture, the optics really is defined by the f number of the lens and the aperture, or the size of the diameter of the lens itself. The lens blur, or in other words, the smallest spot size that you can capture, is really fundamentally limited by the f number of length of the lens and the wavelength of light. These are the two things that really control how small the lens blur is. So you want to make a very sharp lens, you want a really low f number lens, as long as it's diffraction limited. And so, together with the diameter of the lens, that gives you an idea as to how much information you can really fit into the lens. So you have a large diameter and a small f number that allows you to fit a lot of information through the optical channels for your sensor to detect. Now when you reduce that to a smaller aperture lens, as you do with an array camera, because you have a limited amount of space for yourself to start with, you're reducing the amount of, as long as you keep the f number the same, which you can, the lens blur remains the same, but because the diameter is much reduced, the amount of information that you can now fit in has been reduced significantly. And that's what that equation looks very complicated, but essentially that's what it says, that the smaller the f number, by virtue of the fact that you have a smaller lens blur, you can fit more of the information in the available space. But you can actually recover a lot of the information because of aliasing. And aliasing is a phenomenon that people in signal processing are fairly familiar with, which is signals that are at our set frequency end up getting erroneously sampled by the fundamental limitation of the sampling process, that as a result of which the frequencies appear as a lower frequency, masquerading as a lower frequency. And the advantage here is, with an array camera, because of the positional change of the camera in the array, each of the cameras in the array actually has a slightly different aliasing pattern, and the information that is lost, supposedly, in the reduction is actually still there, the aliased information, aliased part of the spectrum. So by combining all these information, the aliased information from the different cameras, you can actually recover much of the information that is hidden in the process of downsampling lens. So what you get from the array camera is really a a set of low-resolution images, and the pipeline that is used today to process these images is a little different from what you have in the conventional camera. The conventional camera has a Bayer filter, so you have a mosaic pattern of red, green, and blue pixels on your device. So what comes out of the camera is an image array with red, green, and blue pixels interspersed, which are then interpolated to get the true color. So, but here you have different low-resolution images, all from different points of view, and you have to correlate the images across each other to determine the depth, and from the depth, you can then fuse the images onto a common grid to get a super resolved image. And once you have a super resolved image, you have the advantage that you now have a full color image with depth in every pixel that you can process in a much more controlled way through all the color sharpening and the color processing that every other camera has. And you can output a JPEG image, and you can even fold in the depth information as part of the JPEG file, so you maintain some amount of backward compatibility with existing file formats. Now, the resolution of the camera array is no different in terms of the parameters that it depends on. It is still dependent, just like the regular camera, it's dependent on the optical format. That is the size of each camera in the array. The number of cameras also make a difference. The F number of the lens controls the lens blur. There is also a pixel blur that comes from the size of the pixels. So the smaller the pixels, the less the pixel blur. And that's actually an advantage to smaller pixels, although you lose light sensitivity. And finally, of course, there is a certain amount of improvement in resolution you get by super resolving the low resolution images, and that is the super resolution factor. Now, this image that you see points to an interesting phenomenon. When you draw lines from, so this represents an array of cameras on a common plane, and you have each camera is capturing a field of view. And when you draw lines that span the field of view of each camera, you'll notice that these lines intersect at regular intervals from the camera array. And those regions, for example, over here and here and here, are regions where the cameras literally fall on top of each other, which means there is no additional information that any one camera in the array has over the other cameras in the array. And as a result, in those regions we call as null spaces, you don't really get any super resolution. You don't get much super resolution in those places. But thankfully, the manufacturing tolerances are sufficient that, this is only true if you have a perfect idealized system where every camera has the same distortion as the other camera in the array. But the manufacturing tolerances, of course, prevent that, and that's one of the nice things. And so these things are kind of scrambled in reality. But even so, you can see that the more the cameras in the array, the better the sampling diversity and the better the resolution recovery overall. Let me just fast forward here through some of the animations. The image on the left top is an image of a high frequency pattern from one of the cameras in the array, and you can see how aliased it is. There's not really a whole lot of clarity in the signals. The numbers here, 6, 8, 10, tell you the number of line widths or line pairs per unit. In this case, line widths per picture height, or you can convert that to line pairs per millimeter. So this is 600 line widths per picture height, 800, 1,000. This one is 500. So you can see that in this case, the low resolution image, the maximum observable frequency is somewhere in the neighborhood of about a little less than 500. It's about 480 actually. Now this blue curve represents the resolution contrast of the low resolution image. Now after the super resolution, you have clarity in the patterns. The signals have been recovered. And you now can actually observe frequencies all the way to beyond 1100. And that is reflected by the red resolution curve, which is, as you can see, significantly higher than the low resolution image. In terms of the maximum observable frequency, it's about 1140, and together you can compute that the overall increase in super resolution as a result of combining these images is about 2.4. It gives you a sense as to how much resolution you can recover through this process. In reality, we find that there is a limit to how much super resolution you have. It's about 2.5, as you can see here. Beyond this amount, no number of additional cameras can result in any further resolution increase, although it can be an advantage in terms of signal noise ratio. Here's an animation which just shows how, when you throw these different cameras on a common grid, how the resolution increases step by step. And that's the pilot estimate, the all in greens. Finally, the super resolved color image, as you can see. So now let's look at a few results from this kind of architecture. So we have actually also, in the previous slide, if I just go back, the thing I want to point out is that the F number of the lens that we are looking at here is an f3.1 lens. In comparison to an iPhone 5S or a Samsung Galaxy S4, they are typically in the range of f2.4 to f2.0, so they are much sharper lenses. The pixel size, which contributes to the pixel blur, is about 1.75 microns. The pixels in the latest generation of phones are about 1.4. So there is also a curve here that shows the resolution curve for the iPhone, and it gives you an idea as to why the iPhone has significantly higher resolution than the darker resolution from the array camera. But the fact is that the array camera has room to grow. The resolution can scale if you go to a smaller F number and a smaller pixel. There is no reason why this can't meet the same resolution as what we have in the conventional camera. Now, when you have, so here's an image that was taken outdoors. This is the high resolution image with the camera array. This is the, this is the taken with the iPhone 5, and this is the same image taken with the camera array at the same time. If you zoom into a certain region, you can actually see that the iPhone 5 is sharper as a result of a sharper lens and a smaller pixel blur. Interestingly, when you take the picture indoors, there is an interesting effect that happens that is worth looking at, and that comes down to the depth of field. So the iPhone 5S, because it has a much larger aperture, it actually has a fairly limited depth of field. So when you take pictures at close range, at the point of focus, the image is very sharp, but there is defocus away from that point of focus because of the limited depth of field. Here's the same, the array camera, from the same point of view. There's a field of view difference between the two cameras, so you see that's a difference you see, but it's the same lighting conditions. But if you zoom into the areas, you notice that at the point of focus, the iPhone 5 is sharper than the camera array. But as you go away from the point of focus, the camera array, because it captures everything in focus, there's no lens defocus, and it actually stays sharp all the way through. And as a result, on close-up shots and portrait shots, you can actually get, the perception is of a sharper image with the camera array, even though it has a slower lens and a higher pixel blur than what you get with the conventional camera. The process, the super resolution process and the image reconstruction process is very robust, even in the presence of noise, because you have the advantage of multiple cameras that provide a certain amount of thresholding against the noise. And so this is the image from one of the cameras in the array. And after the reconstruction, it gives you the color image, and you can see the amount of cleanup in the noise, especially in the background with the white wall, for instance. Well, besides the images themselves, you also get the depth at every pixel. Now, it is a passive system, and like a lot of the depth cameras that are out there today, like what you have in the KINECT, which are active systems in the sense that you're actually projecting light and using the pattern in front of you to compute the depth of the optics. There's no projection of light here in the camera. pixel disparities across the different cameras in the array. So what you get is you get very high confidence depth where there's texture, but in the regions where there's no texture, that's in the flat regions, you get a lot of noise in the depth. But that noise can be filtered out, and you get a high confidence depth map that you see here. And because you have depth only on the textured surfaces, you can actually, by correlating the color of the pixels in the local neighborhood, you can regularize the depth to fill in the missing depth regions and get a depth map similar to what you would get from a KINECT. And this kind of depth is actually very useful, and it can support a lot of applications that are not possible otherwise. The other advantage over here is that in the case of a projected system or an active system, you typically have a colored camera and you have an IR camera, which is going to sense the IR patterns that are being projected. And these two cameras have a slightly different viewing position. So the depth that you get from the IR camera is not co-located with the color camera. And it's also a fairly low resolution. Whereas here, you can actually get the depth co-located with the color image. It allows you to capture the texture as well as the depth coordinates without loss of accuracy. So let's look at what this depth can enable us to do. What are the kind of applications it supports? So we talked about the fact that the camera captures a large depth of field image, and but the fact is that you also have a depth at every pixel. So if you do want to have a synthetic focus effect, because it has some artistic advantages, you can introduce a defocus blur selectively on different depth. So you can actually focus on the rear, or the middle, or the front after you capture. So the advantage here, of course, is you don't suffer from autofocus lag, and the picture that you capture is the picture that you want because you get it at the instant you click the shutter. So what else can this do? Now, one of the things that is important in a number of applications, including, for instance, in video conferencing, is the ability to extract the foreground so that you can replace the foreground, the background, with another background, composite it onto a different background. So there are many reasons why people want to do this, either for privacy or other reasons. But it's very difficult to do that. It's difficult to do that because the ability to determine which are the foreground pixels and which are the background pixels it's not easy. It's a very compute-intensive process. And fundamentally or mathematically, the problem can be expressed with this equation that you see, which is really a combination of the foreground and the background pixels modulated by the transparency factor, which is alpha. So what this says is that if you have a pixel that belongs only to the foreground object, the alpha value for that is 1, and vice versa, which means that the pixel only belongs to the background object, the alpha value is 0. If, however, there are pixels which are partially covered by the foreground object, then this alpha value is between 0 and 1. And those are the pixels that are very difficult to determine. And we have tried, I'm sure many of you have tried doing this in Photoshop, where you have to, and it's a very under-constrained problem, so it requires user intervention. The user has to specify the boundary regions that they want to segment out of the image. And it takes time. Now, the region of uncertainty is called a trimap. And this is the region where the alpha values are neither 0 nor 1, it's somewhere in between, which means those pixels are partially covered by the foreground object. And estimating them is a mathematically difficult or computationally difficult problem. But once you've determined where the trimap is, because the trimap region is really a localized region around the foreground object, it becomes much more tractable because the number of pixels are much smaller than the overall size of the image. With camera arrays, there is an intrinsic advantage because the visibility of the pixels gives us a clue as to what this region of trimap is. regions in this picture. So here's the foreground object, and here's a couple of background objects. And there are shaded regions around the foreground object where only a limited number of cameras can actually see these regions. And in other words, not all cameras in the array can see these regions because they are partially occluded by the foreground object in front of it. And these are regions that are immediately computed because you have information from multiple cameras, and it comes out of the depth map computation. So that gives you immediately a trimap region that you can then localize. The problem becomes much more constrained. It is not over-constrained, but it's not under-constrained either. And you can actually quickly come up with a solution to determine or extract the foreground from the background. So you take an image from the camera array. The regularized depth map is shown here. As part of this depth computation process, you are computing the trimap, and from the trimap, you can actually extract the map. And it gives you sub-pixel accuracy, so even small features like hair get pulled out correctly. Now, this happens automatically. So this is a fairly big advantage when it comes to applications requiring image editing, for instance. So here's an actual image taken with the subject in front of a textured background. The map is computed, and you can composite it onto a different image. Or you could edit things depth layer by depth layer, where you can extract a map, and you can then composite it onto a grayscale background. You can even use the same background as before and convert that into a grayscale image, so you have more of an artistic control in how you want the image to appear finally. Distortion correction is another important area. We're all familiar with the selfie phenomenon, where we take pictures of ourselves. The problem is, at close ranges, there's a lot of perspective distortion. The image doesn't quite reflect you because your face is distorted by the closeness of the objects to the subject. But now with the depth map available, we can actually correct for those distortions. And that has a much more, the consumer experience or the user experience is much improved. So this is the image without the distortion, with the distortion as you capture it. And once you correct for distortion, this is actually the true image. So you can envision a potential video conferencing system that might become available, where it enables real-time background substitution to enhance privacy, perspective correction for facial distortion, and the third one is gaze correction, because this is particularly annoying for people who have been doing Skype videos or any kind of video on your laptops, where the camera is located on the top of the bezel. You're looking at the window where the person you're communicating with is, and the person who's looking at you gets a feeling that you're looking somewhere else. It's a very disconcerting feeling. That can be fixed with the availability of the depth. So I wanted to quickly show some of the differences between the depth that you get from the passive systems such as this compared to the KINECT depth maps that we are familiar with now. So if you look at the way depth is computed, we are computing depth not from a projected pattern, but we are computing it from correspondences across the different images in the array. And triangulation of these different pixels allow you to compute depth reasonably accurately at close distances. And then you regularize the depth to fill in the missing regions. And so this can potentially have in applications in 3D scanning, for instance. You can map out the interior of the space and also potentially detect motion. So in other words, the camera will not be fooled by shadows moving across the scene and responding to that because the depth of those shadows can be a disambiguating factor. So here's some images taken with both the KINECT and the camera array, where you can see that in the case of the KINECT, 1.5 meter distance fluorescent lighting. The backpack of the person actually difficult to disambiguate because the interesting thing is with IR cameras, the reflectivity of IR cameras is not the same as the reflectivity for the visible light spectra, and objects that appear one way in visible light actually appear very different in near IR. And as a result of that, sometimes it can get very difficult to disambiguate between clothing. Whereas with the passive system, of course, what you see is what you get, and you can actually tell clearly what the person's carrying. As the object proceeds at farther distances out, you can see in the case of the KINECT, the head has gotten chopped off. A lot of the reasons for that is actually IR sometimes has a difficult time with hair. The reflectivity of hair in the IR space is sometimes challenging. Whereas in the case of the passive system, you still have a clear discrimination between the person and the clothing. Outdoors, it's a completely different issue. IR is overwhelmed with the amount of IR light that the sun has. It doesn't work, and it's the same problem with the time-of-flight sensors. And this really is where the passive system has the biggest advantage, because the better the light, the lower the noise, the better the net. So this is again a reflection of how the triangulation allows you to determine the distance to objects. So you can see that the disparity between the pixels in the two cameras changes with the distance of the object. And that change in disparity allows you to compute the depth through a triangulation. Now, to give you a sense of how the depth accuracy changes, the depth really is fundamentally determined by three factors. It's determined by the separation between the cameras and the ring, the size of the pixel, and the focal length of the lens. The most important factor is, of course, the distance between the cameras. So the larger the distance, you have more disparity, which means that you can actually disambiguate distances out to further out, and you can get good accuracy. Smaller the pixels, you get more depth accuracy, and larger the focal length, you get more depth accuracy for the obvious reasons from the picture that we showed earlier. And so, for instance, if you had cameras that are separated by 3.69 millimeters compared to 5 millimeters, you can see how the depth accuracy changes with distance. So for instance, at 5 meters, the difference in accuracy is 30%, 35% in one case and 50% in the other case. But at close distances, less than a meter, it can be accurate within millimeters, which is really very good for scanning. So here's a picture of a dragon that we captured at fairly close range. Highly textured objects, so we could actually get the depth, and we imported that into a 3D viewer. These are not triangulated, this is just a point cloud, but triangulation is a fairly simple step from here. So it's easy to see how this can very easily be used as a 3D scanning device. So what you have now is a camera that can be both a 2D imager as well as a 3D imager, and works on all conditions. The other advantage, of course, is that when you capture an image, you're capturing, in this case, you have 16 cameras, and you have a large synthetic aperture, so you're capturing from different points of view. And there's a fair amount of disparity between the different points of view, as you can see. And all of this is being captured at a single shot. So when you reconstruct the high-resolution image, you can reconstruct that from any point on the large synthetic aperture that allows you to give a living picture which you can interact with. It's a more natural picture that you can correct automatically for the distortion, change the background, and view it from slightly different points of view. We talked about low light imaging, and we talked about if you wanted to extend the sampling to beyond the visible light and to go into the near IR part of the spectrum, what does it give you? What are the advantages? It turns out that there is actually a lot of signal in the near IR part of the spectrum that we are not utilizing today. And that can actually be very useful in some ways. So if you look at this image that was captured, now this part, the graph from 400 all the way to 650 is the part of the light that we actually see. Beyond 650, the eye can actually probably see till about 700, but 650 is the range at which all the cameras cut off. And beyond 650, there is actually a fair amount of signal, as you can see by the intensity of the signal that the graph shows, or the picture shows, that is simply not used by the cameras today. And the reason is that if they did let that signal in, because the eye doesn't see that signal, allowing it in and capturing it and making it a part of the picture would actually corrupt the color, so you would actually see a false color image, which doesn't really lend itself to consumer viewing. So the question is, what can we do to improve the experience in low light? It turns out that because the cameras are all optically isolated, you can actually capture the near IR part of the spectrum by sensitizing just some of the cameras to near IR. And that information is available so that you can selectively use that information to denoise the color image that you do create. And that actually gives you a significant amount of advantage in low light situations. So the other advantage, of course, is that because you're independently controlling the cameras in the array, you can actually compensate for the transmissive differences and the sensitivity differences between the different cameras for the different spectra, and ensure that the proper amount of light is set in. So here's an image that was captured in 300 lux, which is fairly good lighting, room lighting, if you will. So this is the image captured with just the RGB part of the array. There is no near IR involved. It's very good lighting, and as you can see, the recreation of the region of interest that is shown below that is very good. It's not very noisy. If you add the near IR component, it's very similar, which is as it should be, because you don't want the color to be corrupted with the addition of the near IR component to the image. But it's in low light that it really comes through. Here's the same image in low light with just the RGB part of the image. And you throw in the near IR, and that's what you get. If you go back to the image over here, there's not a significant difference between the image at 300 lux and the one at 20 lux. And this can be a compelling advantage that will enable us to capture good images in low light with an array approach that the industry is still struggling with as far as conventional camera goes. And you can do this without flash. You can conceivably think of flash in the near IR spectra, so you don't even see the flash going off to blind you, what you call dark flash, for instance. Here's a blown up part of the column in red chart. This is just the RGB part of the spectrum, and this is the RGB near IR part of the spectrum. And if you notice on the previous slides, the CMOS sensor actually has good sensitivity till about 1100 nanometers, and we are capturing information only till about 800 nanometers, so there's still a good rate of signal that we can still use to go even lower. So in conclusion, there are a bunch of ecosystem dependencies that needs to come together, and is coming together as we see, for this to become a reality. Optics are now being addressed to manufacture the optics in array format. The small pixels that the conventional camera industry has been spearheading has advantages for the array camera as well, because it reduces the pixel blur. Packaging technologies that allow you to mount lens arrays to sensor arrays directly. The amount of computation you need to do has been the biggest challenge, and that's where the industry has really been stepping it up over the last few years with the quad-core GPUs compute power than a desktop had a few years ago. And that really helps. We believe depth is the next modality, and we can hopefully look forward to getting depth on our cell phones in the not too far future. And the combination of form factor, robustness in imaging, and passive depth acquisition, we think, represents a pretty compelling situation going forward. Thank you.
For sharing your work, fascinating physics and electronics there. Are there advantages? You got a 4x4 array. Might there be advantages to having greater spatial distance between 2x2 arrays or 3x3 arrays for mobile devices?
This is just a reference design, and clearly you can go to any sized array. Now, you notice that we are actually separating the color channels. So you're having separate cameras for green, separate for red, and separate for blues. It turns out, to ensure that you can recreate the full color image without artifacts, you need a certain minimum number of cameras for each spectral channel. So 2x2 really doesn't do it. You still have artifacts. But a 3x3 is certainly possible. And we have experimented with 3x3s or 5x5s. Or you can even have linear arrays. You can have 1x9s, for instance. And you can have two of them that allow you to get depth out to much farther distances. So all of those are possible.
So what do you roughly end up with then in terms of the increase in the number of bits per pixel versus the traditional photography? And how will that scale then if you increase the total number of megapixels per image?
Yeah. To clarify your question, I think you're talking about the overhead.
Yes, related to the storage capacity.
Yes. The overhead really here is the depth component. So you're getting a depth for every pixel. But that depth, it turns out, we can actually compress that quite a bit. And we find that it increases the JPEG storage requirements by about anywhere from 30 to 50%. So if you have an 8 megapixel image, an 8 megapixel image converts to about a 2.5 megabyte JPEG image. With the depth thrown in, that becomes about 3.2 megabytes. 3 to 3.2.
So I appreciate your ability to extend the dynamic range by bringing in the IR. Have you also considered the idea of patterning some neutral density filters over the array so that you can further extend the dynamic range?
Sure. That's actually a good point. It turns out that we can certainly do that, and it's certainly possible. But we actually enable dynamic range extension by changing the exposure of the different cameras in the array, so you can capture multiple exposures simultaneously. And this allows you to get the high dynamic range without suffering from some of the motion artifacts, either in the scene or in the hand motion when you capture it.
Final question.
Do you see this technique being swapped over from mobile devices to bigger devices?
We are getting a lot of interest from other application spaces. Well, automotive is one area, webcams, smart TVs, and as well as the movie industry, they see a lot of advantage in getting depth for post-production reasons. There's no reason theoretically why this doesn't scale with the size of the lenses, and the only thing is the computational limitations. But if you go to other markets, you certainly have a lot more compute power circuits.
Well, we have to leave it at that, unfortunately. It's a very stimulating talk and a very stimulating subject. I can't believe that Kartik will be around for a little bit for answering any further questions. And there is some kind of demonstration that you can see here as well.
Just one comment I want to make, which is there is a demo here with the array camera running on a Qualcomm Android tablet. So my colleague and I will be happy to show it to you if you want to come after offline.
So it just remains for me to thank Kartik Venkataraman for a stimulating talk. Thank you very much for joining us.
Thanks,